Swayam Prabha. Digital India. Educated India.
So again some probability. So if we can learn a function which you give the output of these curves, like one of these curve which I have already drawn. So if this curve is our fx, so this curve is probability of y equal to 1 given x. If we can learn this curve, this regression or this probability distribution function, and this is a posterior probability distribution function, then we are done. So if this probability is greater than 0.5, then it will be class 1. If it is less than 0.5, then it will be class 0. Okay? So now how we can get such a nice curve? This nice curve is not linear. Is it linear? No. This is not a linear. Even this is not a convex. So it is called the sigmoid curve. So if we can learn this curve, then we are done. So if we have some function like W transpose X, so it is do you know what is this W transpose X means? This is inner product, dot product, okay. So W is in the same dimensions where the X is, so both the W and the X are in RD, and the B is the bias. Right? And now this is a linear thing. Now if we have one sigmoid function, so the sigmoid function of the z will be something like this, 1 by 1 plus e to the power minus z, where maybe the z equal to this. Then if we have some graph, here it is the z, and then sigmoid curve will be like this. This is h. So we'll be using this sigmoid curve to learn our fx, this posterior probability. So I think this thing you have already learned a little bit of Bayes theorem. So if we have a posterior probability, this is p y equal to 1 given x, then you can write it as a, this is called the likelihood, or it is the class density. In the classification problem, it is called the class density, and then that means the density of the sample x when class is given. The denominator will have the sum over all the densities, so which is also okay. So another term is here. This is called the class probability or the prior. This is what is the probability of y equal to 1. So according to the Bayes rule, if you remember, so the g star of x was equal to 1 if the probability of y equal to 1 given x is greater than the probability of y zero given x. So if we apply the Bayes rule here, it will be something like so this is the class density of class 1 and this is the prior of class 1. and this is the class density of class 0, and this is the prior of class 0. So we can say that this will be if this class density of class 1 by the class density of class 0 is going to be greater than this, then this thing will be 1. Otherwise it will be 0. So we know, so there are many type of models which can, yes, last slide.
What are we referring to this pi naught pi 1?
Okay, so this is the, so this is the probability of y equal to 0 given x, sorry, y equal to 0. This is the prior probability of the class.
And z refers to sum of all the prior probabilities. Z refers to sum of all the prior probabilities.
No, z reflects to all sum of this all. Okay. So first we'll learn that one thing, it is called logistic regression. So where there we'll learn this regression which will give you this fx, which is a nice this sigmoid shaped curve, and it will give the it will actually predict the posterior probability of your class 1, and other this, and then we'll put it into the base rule, and then we can get it the classifier. Other than this, we can do other things, which is where we'll actually optimize or estimate the density, and then estimate this class density with the from the D. So we'll learn it's later. So first we'll focus on this regression based things. And then another thing, another type of classifier is there, which is with very famous support vector machines, which does not deals with at all this probability or the class density or the priority, is totally optimization based classifier. So there we'll choose, we will have a lots of classifier where from will be choose the best one which fit. So it is so we'll see that later. So now what is the linear classifier? So linear classifier is a classifier like you this is the same problem, it's this iris data set plot. If you plot two features which are the sepal width and the petal width, and these colors are the three classes, Setosa, versicolor and virginica. So there we have some boundary. If you see the second plot, where the boundaries are the linear in the space, and then this is called the linear classifier. So we have to find out this linear separator of in the space, so that any points if it comes here, maybe we can say it is a blue classifier, blue class from the same class. So this will have already seen that this sigmoid curve. And now if we have a linear function which is W0 W transpose X, and then we put it in the sigmoid function, this linear function, and then we'll get that posterior function fx, and so this will be the fwx. This is parameter is w, which we don't know, maybe we have to learn when we learn the classifier. And then this is going to give you this posterior density of class 1, and this with the sigmoid function it will be looks like this. And similarly then y equal to 0 given x, it will be 1 minus fx, the probability is like 1 minus probability of class 1, the probability of class 0, and therefore it will look like this. And so if you put these things in the base rule, then if you think that this one, This one, both the cases, the denominator are the same. So only the things will be this, the above part. So if this part is greater than 1, then it will be class 1, right? So therefore, we'll put it in the log. If this thing we put, then it comes to, maybe I should go back. Remember, this probability of y equal to 1 given x, it is equal to f wx, and this is equal to x to the power x e to the power w 0 plus w transpose x and by something, and then probability of y equal to 0 given x is equal to f of one minus this, and this is going to be this plus same things. So do you remember now this base rule? It will be 1 if p of y equal to 1 given x is greater than p of y equal to 0 given x, right? Okay. So in therefore we can say that if e to the power w0 plus w transpose x is greater than 1, right? Do you remember this thing, how it was? So this was the same, and this is, and so this is, you can write that this x is greater than 0 because this is e to the power 0, right? Right? So we take both sides the log and we'll get this, right? So you can also put a equality here. So actually our decision boundary is then on depending on a value of a linear function, linear over x, the sample. So this is a linear function, linear over the sample, and the decision boundary is changed to, like, if this linear function has the value greater than 0, then it will be class 1, and it is, if it is less than 0, then it will be class 0. So though we are fitting a non-convex curve with a non-linear curve, but using the sigmoid functions, and it turns out to be we are actually doing the linear classification because this is the our linear boundary. Okay. So this function of this log function here, this is called log odds ratio, and that is why we call this model as a logistic regression. So but what will be the loss function, what we want to optimize, what we want to minimize? As you have minimized for the regression the square loss, how we will calculate the loss function for logistic regression? So it is clear that why logistic regression is a linear classifier, and why this type of regression we can use as a classification, right? Okay. Now see the what is the error, what is the loss, and so the while running. So here we don't know w. What is the w? W is the parameter. So we have to learn w when we will be learning the classifier. It's clear? Okay, then how to learn the w? How you have learned this w or beta for the regression parameter? You have minimized the regression loss or L2 loss. So here also we will be have to minimize some loss, that is a classification loss. So now if you think like if we can write in these things, what is the class posterior density of the class? It's going to be this fx to the power y and 1 minus fx to the power 1 minus y. So when y is in 0 and 1 class it is coming from, then probability of y equal to 1 given x is equal to fx, and we can write this fx equal to f, this is to the power y to the power 1, And this thing also, so maybe I should again go back here. So probability of y equal to 1 given x equal to fx, and this is going to be the probability of fx to the power y as y equal to 1 here, and other thing is probability of y equal to 0 x is going to be 1 minus fx to the power 1, and here the y equal to 0, so it is going to be right, because here the y is equal to 0. So we want to maximize this probability, right? Do you realize that we want to maximize this? Everybody? And so we want to maximize it for all the data, and therefore when the data are independent, we can take the joint probability as a multiplications over the data, right? And then the thing is that we'll have this we'll be having the maximizing the log likelihood, and therefore we'll be minimizing the negative log likelihood. So the maximizing the log likelihood will be equal to the negative of minimizing the negative log likelihood. And so this is going to be our loss function. So here I just put now you replace this fx as equal to w0 plus w transpose x, and then we'll get this function. So here we want to minimize therefore this function. Now you know what is logistic regression, right? Do you think anything else we need to hear? Okay. So now I'll give one more example to you. This is some sample, training sample. Now how is your this curve should be? I'll draw two curves for you, the training curve. One is this one, and other is this one. What is the better one? Why?
Because it's more generalized concept in comparison to the yellow one.
Why you are saying it is more generalized?
Because it do have an error, valid do have an error, but on an average it's having more points for blue as well as for red, more space for blue as well as red. But in comparison to the yellow curve, it's making a specialized model for keeping all the red at one side, having less space for the blue and more space for the red.
Okay. So now what will be your classifier if you minimize these things? So you are going to minimize this log what we call this log likelihood. Where you want to go to minimize log of this probability of y equal to y given x. Do you remember that previous formulations? It turns to be something log of some function of some h function of w0 and w transpose. So if you just minimize this likelihood with the sample, which curve you will get? The orange one or the magenta one? if you just minimize the loss or if you just maximize the likelihood? Orange one you will get, right? But you are saying that orange one may be, this point may be some error, so we should not give that point some weightage. We should have more smoother curve for our generalization. Then we need to fit some other term there, which is called, what is called? Regularization. So now we'll put these terms of regularization, and then this is going to be our logistic regression with the regularization. What here we are doing by this regularization term is that we are minimizing the norm of the W, the classifier, that will make the classifier more like, as he said, like it will give weightage to the both the classifier equally. Okay. 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 So it's in general we use L2 norm. L2 is not the loss here, right? So here you have, this part is the loss part. This is some log of exponential of a linear function. This function is not a linear function. But this part is our regularization. Here you can use any norm, but it is in general it is mostly use L2 norm. There are some things like when we want to do some kind of feature selection, if you think about lasso kind of things, where we want only the few W to be getting non-zero value and the most of the W get the zero value, then we will get L1 norm. Okay, now until now we have learned the logistic regression for the binary classifiers. So, but what happen if we have more than one class? Before that, maybe we'll go through once more what we have learned here. Like what is the classification task? Anybody can tell me? So this is one kind of supervised learning, and where we have some training data and with the label, and the label is discrete. Some few categories are there, then we call this as a classification task. Can we solve the classification task with the regression? It is better not to, because we will have different kind. One thing is we will have different kind of loss. Another thing is, like if we use any linear regression and then put a threshold, then it may create some problem. So we'll have some different loss for the classification. So what is the loss for the classification? Generally use 0, 1 loss. And where it is 0, the loss is 0 when we are correctly classifying, and loss is 1 when it is wrongly classified. So can we have something else than 0, 1 loss? Sometimes we have something else than the 0, 1 loss. It can be 0 and some number, some weight. So that, like think about this classification task of whether some patients is Nipah infected or not. So here we do not have the same loss for both the misclassification. If somebody is positive and we classify him as a negative, then it will have more impact. So this loss should have more penalty. While somebody is actually negative but we classify as a positive, it will give us a one little bit expensive things, maybe we have to go for a test for him, but still it is safer. So in that cases we sometimes have the bias or weighted losses, and then it may not be exactly the 0, 1. Okay? Okay. And then when we can learn a regression which can be bounded within a 0, 1, and then we can say that we are predicting the posterior distribution of y equal to 1 given x. If we can learn that function, that probability distribution of y equal to 1 given x, then that is a regression function, and then this function we can put into the Bayes rule, and then we can get the classification task done. So, one such function can be learned by using sigmoid function over a linear function. So, now we want to fit a sigmoid curve over a linear function. We want to fit it such that it predicts the posterior probability of y equal to 1, and therefore we increase, or we want to maximize, we want to learn this w, this linear function, such that this predicted probability has the maximum likelihood relations with the actual data. And when we are doing this maximum likelihood, that means if we minimize the log likelihood, it will be doing the same task. So, therefore, we are doing the minimizing the log likelihood of this predicted function. And we also know that if we only minimize the loss, there will be some sort of overfitting. There will be a chance of some sort of overfitting on the samples. So, you all know, you have learned that we will be reducing the bias, but the variance will be increased depending on the samples. So, it is better to put some regularization on our, or you can think about it is some type of constraint on our parameter. So, with the addition to this constraint, we will get the full optimization function which we want to minimize to learn logistic regression. And where is this, what is the C here, you know? Just think, if your C is infinite, then what will be the effect? You will be, yes, there will be no effect of regularization term. You will be only minimizing the negative log likelihood, right? And if your C is 0, then you will be giving a huge weight to the regularization term, and you will not at all put any weightage on the loss, actual loss. So, C is a user defined parameter, hyperparameter you can say, and that you can decide on the data like what weightage you want to give on the regularization and what weightage you want to give on the actual loss. So, what kind of overfitting you will be allowing, and after what you will not stop it, right? How you choose a C? How do try it? So, you will have some training okay, you tell me how you will try it. Okay, so you all know about what is the cross validation? Yes, good. So, even if you don't do the cross validation, if you have some data other than the training data, you have to keep it aside as a validation set. Okay. And then you have to, after your learning your model on the training data, now you test your your model with the help of this validation set. So, we will be assuming this validation set is a representative of our test data which is unseen, and then for which parameter C this validation data is giving the lesser error, will be choose that thing. So, now this is the difference. So, previously this was the linear regression curve which we thought of learning with the data, but then we change our decisions and we thought of learning something else, and will be some sigmoid curve, and this is going to be give our logistic regression.